Hello, my name is James Morton, and I'm excited to share our work on obtaining protein structural alignments from sequence using deep neural networks. Here we introduce a new framework, DeepBlast, which is an end-to-end sequence alignment method to infer protein structural alignments from sequence. Protein structural alignment can be useful for measuring differences between proteins due to their structures, which are not inherently clear from their sequence alone. Previous works that focused on measuring protein similarity fall into two distinct camps. One set of methods focuses on measuring sequence similarity using edit distance-like metrics to determine how many mutations occur between two proteins. Another group of efforts use the protein structures to physically superimpose two proteins on top of each other to see how well the structures line up. Unfortunately, the vast majority of proteins do not have structures. So these types of structural alignment methods are limited to those proteins with experimental structures. Fortunately, there's much promise from recent developments utilizing methods inspired by natural language processing that can predict protein structures from sequence and hold opportunities for bridging this gap. Our contribution here is that we show that deep learning methods can be used to augment sequence alignment methods using differentiable dynamic programming. And then we showed that these new class of algorithms can outperform the existing sequence alignment methods and perform comparable to protein structural alignment methods. Our model design can be split into two parts. First, we can use neural networks to learn the alignment scoring parameters that can be later evaluated for dynamic programming. Once we have the scoring parameters learned, we can then use a differentiable analog of the Needleman-Wunsch algorithm to predict the expected alignment between two sequences. Here's a high-level overview of our model. Our model takes two proteins as input and will then use those proteins and generate an alignment. The goal here is to tune the neural network weights to minimize this classification objective. Here, we're trying to maximize the accuracy of correctly aligning two positions between two proteins. In practice, this works pretty well. As you can see on the left, our algorithm is able to recapitulate structural alignments, even if the sequences are completely different. We can GPU accelerate this algorithm to be practical for most biological applications. As shown on the right, our algorithm is more sensitive than the standard sequence alignment techniques. We're very excited about the biological applications that can be enabled by these types of algorithms. I'd like to thank my co-authors for enabling this work and Simons Foundation for the financial support. For more details, you can see our paper at the following QR code. Thank you.